Imagine a world without liquids. No water to drink, no food to eat, no blood to flow through our veins. It would be a pretty dry place to live. Liquids are essential to life on Earth. They make up about 70% of our bodies and cover about 71% of the Earth's surface. They are also used in a wide variety of applications, from cleaning our homes to powering our cars to manufacturing our products. What are some of the most common liquids that you come into contact with on a daily basis? Some examples of common liquids include water, milk, juice, gasoline, and soap. Liquids are a state of matter in which the particles are held together loosely and can move around more freely. This is why liquids don't have a definite shape, but they do have a definite volume. Liquids can be made up of atoms, molecules, or ions. Can you imagine that a liquid can flow through the narrowest of spaces, even against gravity? Or a liquid that can change its shape to fit any container? These are just a few of the amazing properties of liquids. There are many different types of liquids, including pure liquids. As the name suggests, pure liquids are made up of only one type of particle. For example, water is a pure liquid because it is made up only of water molecules. Solutions. Imagine you have a glass of water. When you mix something like sugar or salt into it and it disappears completely, you've made a solution. In a solution, one thing, like sugar, is mixed so well with another, like water, that you can't see the separate parts. It's all mixed up like when you stir your chocolate milk until it's all one yummy drink. Suspensions. Think about a snow globe with tiny snowflakes inside. Those snowflakes don't mix with the water, they float around in it. A suspension is like that. Tiny things are mixed in a liquid, but they don't completely mix, so you can still see the tiny parts floating around. It's like a tasty smoothie with fruit bits that don't mix in. They float around in the juice. Colloids. Picture whipped cream on top of your hot chocolate. The whipped cream is made up of tiny cream particles mixed in with air. A colloid is when tiny things are mixed into a liquid or gas, but they're not completely mixed like in a solution. Instead, they're spread out in tiny pieces. So, in a way, it's like something in between a solution and a suspension. It's like finding sweet chocolate chips in your cookie dough ice cream. They're there, but not taking over the whole ice cream. Let's learn how they are formed. Liquids can be formed in a variety of ways, including condensation. Condensation is the process by which a gas turns into a liquid. For example, when you see water droplets on the outside of a cold glass, that is because the water vapor in the air has condensed into liquid water. Melting. It is like magic that happens to some things when they get warm. Imagine you have an ice cream cone on a hot summer day. As the sun shines on it, the ice cream starts to get all gooey and turns into a yummy, drippy liquid. That's melting. It's when something solid, like ice or chocolate, gets so warm that it becomes a liquid. Think of it as changing from a frozen solid form to a wet, runny form because of the heat. So the next time you see an ice cube disappear into a puddle of water or your chocolate bar getting soft in your hand, you'll know it's just melting because of the heat. Have you ever thought about what actually is the structure of liquids? Let's talk about it a little. The particles in a liquid are arranged in a random manner. This is why liquids don't have a definite shape. However, the particles in a liquid are still attracted to each other by weak forces. This is why liquids have a definite volume. The properties of liquids at the molecular level are determined by the forces of attraction between the particles. For example, liquids with strong forces of attraction between the particles will have a high viscosity. Liquids with weak forces of attraction between the particles will have a low viscosity. But what is viscosity? Alright, imagine you have two kinds of syrup. One is super thick like honey and the other is thin like water. Viscosity is what tells you how easily something flows. So, when you try to pour that thick honey on your pancakes, it moves slowly because it's sticky and has high viscosity. But when you pour water, it flows quickly because it's not sticky and has low viscosity. It is like the thickness or stickiness of a liquid. Now, a question arises. How do liquids get transformed into gases on heating? When a liquid is heated, the kinetic energy of its particles increases. This means that the particles move faster and collide with each other more frequently. As a result, the particles begin to break free from the liquid surface and escape into the air as a gas. This process is called evaporation. The rate depends on a number of factors, including temperature. The higher the temperature, the faster the particles will move, and the faster the liquid will evaporate. Surface area. The larger the surface area of the liquid, the faster it will evaporate. This is because there are more particles on the surface that can escape into the air. Wind speed. Faster wind speeds will remove the evaporated particles from the surface of the liquid, which will increase the rate of evaporation. And it's inversely proportional to atmospheric humidity in case of water evaporation. Some examples of evaporation are: when you leave a glass of water out on the counter, the water will eventually evaporate because of the heat in the air. When you sweat, the sweat evaporates from your skin because of the heat from your body. When you hang wet clothes outside to dry, the water in the clothes evaporates because of the heat from the sun and the wind. Another way liquids can be transformed into gases is boiling. It is a special type of evaporation that occurs when the entire liquid is heated to its boiling point. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. Another new term, yikes. I'll explain vapor pressure in a simple way. Imagine you have a glass of water. You know how water can turn into steam when it gets hot, right? Well, vapor pressure is like the water's want to turn into steam. You see, even when you don't heat the water, some of it naturally tries to escape into the air as invisible water vapor. This happens because water molecules are always moving around, and some of them have enough energy to break free from the water's surface and become vapor. Vapor pressure is a measure of how much water vapor is pushing to escape from the water into the air. When it's hot, the water molecules have more energy, so they push harder, and the vapor pressure goes up. When it's cold, they have less energy, so they push less, and the vapor pressure goes down. Think of it like a tiny battle between the water molecules that want to escape and the air molecules that want to keep them in. When it's hot, the escape side is winning, and when it's cold, the stay side is winning. So whenever the vapor pressure of a liquid surpasses atmospheric pressure, the liquid starts to boil. So what are the energies involved in these processes? The energy involved in transforming a liquid into a gas is called the latent heat of vaporization. The heat of vaporization is the amount of energy that must be added to 1 mole of a liquid to vaporize it at its boiling point. This heat depends on the strength of the intermolecular forces between the particles. Liquids with strong intermolecular forces have high heats of vaporization, while liquids with weak intermolecular forces have low heats of vaporization. The heat of vaporization of a liquid can be affected by a number of factors, including intermolecular forces. The stronger the intermolecular forces between the particles of a liquid, the higher its heat of vaporization. Molecular mass. Liquids with higher molecular masses tend to have higher heats of vaporization. Now, let us understand how liquids get transformed into solids on cooling. When a liquid is cooled, the kinetic energy of its particles decreases. This means that the particles move slower and collide with each other less frequently. As a result, the particles begin to lose energy and stick together. When enough particles have stuck together, the liquid will solidify. This process is called freezing. The freezing point of a liquid is the temperature at which it freezes. It depends on a number of factors, including pressure. In the case of the majority of solids, the melting point increases with an increase in pressure, as the solid itself is usually more dense than the liquid. When we apply high pressure to it, the pressure helps it to overcome the intermolecular forces of attraction. As it melts, it expands and becomes less dense. Impurities. When we add impurities to the pure substance, the melting point of the solid is decreased because impurities weaken the lattice structure of solids, due to which it becomes less stable and melts before its original melting point. This is called melting point depression. Surface area. The surface area of a liquid can also affect its freezing rate. Liquids with a larger surface area will freeze faster than liquids with a smaller surface area. This is because the particles on the surface of a liquid have fewer bonds to break than the particles in the interior of the liquid. Here are some examples of freezing. When you put water in the freezer, it will freeze into ice because of the cold temperature in the freezer. When you put a can of soda in the refrigerator, it will cool down and eventually freeze because of the cold temperature in the refrigerator. The energy involved in transforming a liquid into a solid is called the heat of fusion. The heat of fusion is the amount of energy that must be removed from 1 mole of a liquid to solidify it at its freezing point. The heat of fusion of a liquid depends on the strength of the intermolecular forces between the particles. Liquids with strong intermolecular forces have high heats of fusion, while liquids with weak intermolecular forces have low heats of fusion. Molecular mass. Liquids with higher molecular masses tend to have higher heats of fusion. Liquids are all around us, and we use them in a variety of ways every day. But did you know that liquids are also used in many innovative and cutting-edge technologies? Here are just a few examples of how liquids are being used in technology today. Liquid crystals. They are used in many electronic devices, such as TVs, computer monitors, and smartphones. Liquid crystals are able to change their orientation when an electric field is applied, which allows them to produce images and text. Liquid batteries. They are a new type of battery that is more efficient and longer-lasting than traditional lithium-ion batteries. Liquid batteries use a liquid electrolyte instead of a solid one, which allows them to store more energy and charge faster. Liquid cooling. It is used in high-performance computers and other electronic devices to keep them from overheating. A cooling pumps a liquid coolant through the device, which absorbs the heat and then dissipates it into the air. Liquid fuel cells. They are a type of fuel cell that uses liquid fuels, such as hydrogen or methanol, to generate electricity. They are more efficient and less polluting than traditional combustion engines. Can you think of any other examples of how liquids are being used in technology? Some other examples include liquid lenses. They are used in some cameras and smartphones to allow for optical zoom without the need for moving parts. Liquid metal. It is a new type of material that has the properties of both a liquid and a metal. Liquid metal is being used to develop new types of robots and other devices. Liquid bioprinting. It is a new type of 3D printing that uses liquids to create living tissue and organs. Liquid bioprinting is being used to develop new treatments for diseases and injuries. Make sure to subscribe for the next episode on gases. Check this episode on solids or click here for the most relevant video for you.